So far we have talked about how to use EMF to create domain-specific metamodels and models that conform to them, and how to then use languages of the Epsilon platform to query, validate, and generate code from such models. In today's final lecture, we're going to touch upon the subject of concrete syntaxes for domain-specific languages. We will start with a brief discussion on textual versus graphical concrete syntaxes, and then we'll talk about some core principles for designing effective graphical syntaxes. We will finish with a brief introduction of Picto, which is a tool provided by Epsilon for generating graphical views from EMF models using model-to-text transformation. In the afternoon's practical, you will have an opportunity to play with Picto and to develop your own model visualizations from a small social network metamodel. So one of the very first steps after defining the metamodel of a domain-specific language is to design the form of the tools that modelers will be provided with in order to be able to create models that conform to our language. And there we are presented mainly with two options. We could either go for a textual syntax or a graphical syntax. Consider, for example, this small language for expressing interactions between objects and users of the system. We could give it either a textual syntax, so this resembles UML sequence diagrams. We could either give it a textual syntax or we could give it a graphical syntax. The information in both representations is exactly the same. We have a user that inserts their card into an ATM, then the ATM requests the PIN from the user provides the PIN, the ATM checks with the bank whether the PIN is valid, and so on and so forth. And if you look at this diagram, it contains exactly the same information. So it's a matter of representation, really. And this is a decision we need to make shortly after we have defined the metamodel of our language. Do we go textual or do we go graphical? If we choose a textual syntax, there are tools such as Xtext, EMFText, SpoofX, or JetBrain MPS that can automate the process of producing parsers and intelligent text editors with nice features such as reference navigation and auto-completion straight from our language. If we decide to go graphical, there are frameworks such as Sirius and GMF and Eugenia that provide significant assistance with developing language-specific graphical editors so that we don't have to start from scratch. So should we choose a graphical or a textual syntax for our DSLs? And as with most big questions, the answer is yes. So what are the advantages of a graphical syntax? 1/3 of our brain is dedicated to processing visual input, which means that graphical syntax tap into this power and make representations much faster to process, just because of the way our visual system works. Diagrams are also essential for engagement with non-computer scientists. Most non-computer scientists will more or less immediately switch off if they are shown a textual representation like this, but they will probably be able to follow a graphical representation like that. On the flip side, a graphical diagram is only editable using a dedicated editor. So if you need someone to make changes to the diagram, you need them to download, install, set up a dedicated graphical editor, and outside of that environment, there are really no possibilities to actually edit the model. And also things that we take for granted when editing text, things like find and replace and regular expressions and copy and paste and being able to comment out a part of our artifact. These are not always straightforward when editing in a graphical mode. Also, version control becomes harder. How do you show the difference between two diagrams like that? These are not completely solved problems. Now, if we opt for a textual syntax, we get the main benefit of being able to use all the tools that have evolved over the last 40-50 years for editing text. So we have a wide variety of text editors for different operating systems, platforms, and so on and so forth. We have powerful tools such as regular expressions, being able to find and replace content, to copy and paste across files. If we feel that our model is too big, we can split it in two files, cut and paste into separate files. We can comment out content, which is very important when you want to try out different alternatives, and practically version control is solved. So we have very good tools for textual files such as Git, SVN, and the like. On the flip side, text is much slower to understand, and the main reason is that we process text in the same way we process sound. It's the same subsystem in our brain. It's the auditory system that processes text. So we need to read the textual specification kind of top down and understand every step. But even if we just have a quick look at the diagram below, for instance, right here, we can immediately tell that there are 3 participants involved in this process, and all of them communicate with each other in some way. This takes significantly more time to achieve by looking at the textual specification. And as I said, text can be inaccessible to many non-computer scientists. So if we work in an interdisciplinary team, or even in a team with other engineers from other disciplines, mechanical engineers, control engineers, etc., text might not be their favorite. Okay, so where does this leave us? If we combine the advantages and the advantages of both approaches, I think we can come to the conclusion that text can be better for editing once we are familiar with a domain-specific language and we're kind of in the zone, we're actively developing models. And this can be the case, this probably my personal opinion, this can be the case even for languages which are traditionally graph-like. So I found that even when designing models that are state machines, for instance, I find it much easier after a little bit to code them in a textual syntax rather than to drag and drop and move edges and add bend points and whatnot. And while text is better for editing, diagrams are clearly better for understanding and for presenting models to a wider audience. So if I was asked to write a model, to develop a model, I would prefer to type it. I would prefer to do it using a textual syntax. But if I was to be presented with a model that someone else has created, I would like to see a graphical view first. So how about implementing both a textual and a graphical editor for our DSL? In this way, we can get the best of both worlds. Well, while this is theoretically possible, given that frameworks such as Xtext and Sirius and GMF, etc., work on top of EMF, in practice it turns out to be quite challenging. And while you will find that there are quite a few prototypes here and there that demonstrate editing models in both modalities, when you look a little bit deeper, you will find that these are mostly quick and dirty prototypes that involve a lot of plumbing and cut many corners. There have also been several PhDs in this area on synchronizing graphical and textual models, but I think it's fair to say that we're still a long way from a robust solution that allows editing in both representations. So if you as a language designer and the developers in your team accept that text is preferable for editing, perhaps a halfway house option could be to use a textual representation for editing your models and then to generate graphical views from that textual representation. If you go down that route, there are 2 main challenges. The first challenge relates to laying out the generated views in a sensible way. For example, if we look at the textual representation of our sequence diagram up here, we won't really find the coordinates of the user icons or the position and width of these arrows down here. This information is nowhere to be seen in our textual representation. And therefore, in order to generate this diagram from this textual specification, we have to compute these positions and these widths and so on and so forth. And this sounds tedious, but don't be scared. There are tools out there that are already good at this and which we can reuse for this purpose. And we'll talk about this later in this lecture. So the second challenge relates to fine-tuning. So even if a program can take this textual representation and transform it into this nice diagram, how can I specify, for instance, that I want the background of the ATM object to be green and not yellow, right, in order for that object to stand out? So let's look at these challenges individually. As I mentioned in the previous slide, in terms of layout, there are several reusable tools out there that do a pretty good job at automated graph layout, including GraphViz, PlantUML, Dagger, and the Eclipse layout kernel, among many. However, to give them a chance to produce a sensible layout, it's important that we keep our diagrams reasonably small. But this is desirable anyway for cognitive reasons. A huge diagram, even if an automated layout gets it perfect, it's very hard to follow. A diagram with lots of connections turns to spaghetti, regardless of the layout algorithm. But we'll talk about why this is important and what we can do about that later on. This leaves us with the problem of fine-tuning, and my view is that this is mostly a matter of expectation. Since graphical modeling tools are very similar to drawing tools, and existing modeling tools provide features for kind of customizing the color and the font of each individual box and arrow, we have come to expect this functionality. On the other hand, for textual programming languages, for example, one hardly expects to be provided with similar functionality. And there's I see no difference, because both graphical and textual languages can be formal, and they can be models and programs can be automatically processed. So there's no fundamental difference. My feeling is that it's mainly a matter of expectation. Yes, fine-tuning would be nice to have, but I think we have more important problems than that. Alright, so having talked about the strengths and weaknesses of textual and graphical syntaxes and how we can combine the best of both worlds through view generation, we'll talk about some principles for designing effective graphical syntaxes, so designing appropriate and useful graphical syntaxes. Fundamentally, when we draw a diagram, we are encoding information that exists in our brain up to that point into a signal, which is the diagram itself, and then this is transmitted to a recipient who then needs to decode our information and reproduce what we had in our brain when we were designing this by reading the diagram. The decoding process, or what happens on the end of the receiver, can be split into two phases. The first phase is what we call perceptual processing, and this is the kind of the field, the information that they get at the first glance, and this is automatic, this is fast, this is highly parallel. This happens in a parallel way in our brains. And then this is followed by what we call cognitive processing, which is the process of actually understanding what is in the diagram. And there you have to kind of look at each box and at each arrow pretty much sequentially. And this can be slower, of course, and it requires more kind of brain power to achieve. So what we're trying to achieve using an effective graphical syntax is we try to offload some of the computation from the expensive phase on the right hand side to the fast and automated and parallel process on the left hand side. So we want to reduce the effort that a reader of a diagram has to spend in order to understand the actual diagram. And there are several principles for designing effective graphical syntaxes. We won't be able to cover all of them. We'll just cover 5 or 6, and then I'll point you to a paper that nicely summarizes the rest. So the first principle is called semiotic clarity, and this dictates that there must be a one-to-one correspondence between symbols and the concepts that they refer to. So our meta model has a number of types, a number of e-classes in emphatic and EMF. We will represent them using a number of different symbols. We want to avoid symbol redundancy, so having multiple symbols for the same construct. So here we can see how C can be represented in terms of the graphical syntax, both as a triangle and an ellipse. This is undesirable in most cases, because when users can start asking, like, why did we choose to represent this instance of C using a triangle and that instance of C using an ellipse, they might attribute the different symbols to kind of different meanings of their underlying model elements when this is not the case. On the flip side, we want to avoid symbol overload, so we want to avoid having several abstract syntax concepts being mapped to the same symbol. We want to avoid symbol excess, so symbols that have really no semantic meaning, and we also want to avoid symbol deficit. So we want to avoid constructs that have no mapping to the graphical syntax. Sometimes this can be done intentionally. We may want to put together several abstract syntax elements into one, into the same node, for example, in our diagram. As long as this is done in a controlled way, this is fine. The second principle is called perceptual discriminability, and it dictates that different symbols should be easily distinguishable from each other. And there are 6 retinal variables and 2 planar variables that we have to play with. So on the retinal side, we can use different shapes, different sizes, different colors, textures, brightness and orientation. And then in terms of the location of a node, we can use different horizontal or different vertical position in a 2D plane. And the more different our visual representations are between them, the easier it is for the users, and the faster it is for the users to understand what's going on, and to create a mental map of our model with very little effort. The third principle is called semantic transparency, and this is the extent to which the meaning of a symbol can be intuitively inferred from its appearance. And there are things that we already have, like, wired in our brain. For example, if we see an A pointing to a B, if we see a node A pointing to a node B, then we intuitively assume that either A comes before B or A causes B. Same if we see these B and C boxes under an A box, that leads us to think that B and C are somehow contained into A, or they are a subset of the A. There are special cases of A. If we see this sort of arrangement, we intuitively think of hierarchy. So A is somehow kind of higher up than B and C. This looks a lot like an organizational chart, for example. And this is what we would immediately associate with intersection. And we want to make use of these kind of built-in assumptions that people have. We don't want to go against them when we're designing a graphical syntaxes. So we could design a graphical syntax, for instance, where where this arrow means that A comes after B, right? That's technically possible, but this would be counterintuitive. It would be annoying for the user to have to remember that, oh, in this stupid notation, it actually means the opposite of what I thought it meant. So I think there are these three nice classifications, starting from semantically immediate, so what we assume that the thing means, it actually means, to semantically perverse, where it actually means the opposite of what you would expect it to mean. I think it's a fact, if you've ever drawn any large enough diagram, it's a fact that diagrams don't scale up well. So they quickly turn into spaghetti that's then very hard to lay out and very hard to understand later on. The solution to this problem is to accept the fact that the person can only understand a diagram of a certain, up to a certain size, and to look at mechanisms for reducing this cognitive overload by breaking complex diagrams into simpler sub-diagrams. And this breakdown can represent hierarchy, or it can represent modularization. And in general, you should strive to have no more than, I think 7 plus minus 2 is perhaps too strict, but any diagram that grows to more than 10, 15, 20 visual elements starts becoming too hard to understand and to properly lay out, even if you lay it out manually. The next principle is called dual coding, and this dictates the use of text in order to complement the graphics. So looking at this notation here, at this graphical notation, where we use edges to represent relationships between concepts, if you look at this representation, you kind of guess that this means many. If you look at the textual encoding, so the equivalent but using text instead of a symbol, that is, so looking at these dots, you kind of guess that, yep, that probably means 3 to 15. But if you have a look at this one, which combines both, it becomes immediately clear, kind of the one reinforces the other. And then it becomes immediately clear, even if you're not familiar with the notation, that this probably means many. So dual coding dictates that using text and graphics together is more effective than using just one of them. So we talked about how it is important for symbols to be distinct and different to each other. However, we should not overdo it. So the last principle we're going to talk about is called graphic economy. And this means that this dictates that the number of different graphical symbols that comprise a concrete graphical syntax should be cognitively manageable. So they should be relatively small, and particularly with reference to particular variables. So if you decide, for example, to only use color to discriminate between the different nodes in your graphical syntax, and you use 32 different shades of green, that's no good, because we can only discriminate between up to 6 categories per variable. So even if you have like 4 or 5 different shades of green, for example, your graphical syntax would be quite hard to memorize. So it's good to make good and diverse combinations of the different retinal variables without depending too much on having squares with rounded corners, with a dashed border. There are other variables you can make use of that will make symbols more easier to discriminate. As I said, we won't be able to cover all the design principles. This content comes from a paper, from a highly cited paper titled "The Physics of Notations," which I would advise that you read before you design a graphical syntax. It's a very useful paper. Okay, any questions so far? I'll look at the chat. Okay, no questions. So we'll move on from theory to practice now. And we'll talk about Picto. So Picto is an Eclipse view for visualizing models using model-to-text transformation in EGL and EGX. These are the model-to-text transformation languages we talked about on Tuesday. And Picto builds on top of existing auto layout, graph auto layout tools such as GraphViz and PlantUML in order to produce nice layouts of graphical views. You can find it as part of Epsilon 1.6, so it should already be included in the Eclipse bundles that you have installed. So one of the key differentiators between Picto and other visualization frameworks, other graphical syntax frameworks in the Eclipse workspace is that with Picto, models and metamodels and visualization transformations and diagrams all live in the same workspace. In contrast to that, tools such as Sirius and Eugenia and Graffiti, they make use of either code generation or they make use of Eclipse extension points, which means that you have to design your language in one Eclipse instance, and then when you want to use your language and you want to create diagrams, you have to fire up a second Eclipse instance from within your Eclipse where your diagram editors become available. And sometimes this is not particularly convenient, especially if you want to only visualize models as opposed to be able to edit them in a graphical representation. So with Picto we can generate multiple views from a single model. Here you can see a small social network model. So we have a very simple meta model with a social network containing many people, and then every person likes and dislikes other people in the network. And here we have a small network of 6 people where Alice likes Bob and Charlie, and then Bob likes Enid and Alice but dislikes Fred and Charlie, and so on and so forth. And what we can see here is one view generated for the entire model, and then we also have focused views for each of the members of the network that show the persons that they like and dislike only, so they kind of focus on a particular person. The way we generate views from models in Picto is through model-to-text transformations. So here we have an EGX rule that says that I want to transform every person in my model through this EGL template into a view that lives under this path in the tree view. So when we run this for Alice, it produces a view that lives under social network Alice, right? So down here, it has this icon, it's of that format, and then it has access to these parameters and it has these layers as well. So it's probably easier to demonstrate this using a live demo, and there is a write-up of this example on the Epsilon website. Under the articles section, there is an article on Picto. So let's switch to Eclipse. Nope. Okay, so what I have here is the social network meta model, where we have the social network class containing many people, and then the person has likes and dislikes relationships to others, and then we have a model that conforms to it, right? So what I'm going to do is we're going to create this, this view now from scratch. So for now I will comment this out. Okay, and we'll start from scratch. So let's create a new folder here, and let's call it Picto Live. So the first thing we're going to do is I'm going to show you how we can use GraphViz to create graphs. GraphViz is an external tool. It's a tool that has existed for maybe 20 years now. It's probably one of the best tools out there for automated graph layout. So I will create a new file, which I'll just call demo.dot. Word will think that it's a Word file. It's not a Word file. I'll just open it using a text editor. And I will ask Picto to render it. So GraphViz provides a textual notation that we can use to define graphs. So I will create a graph that has two nodes, A and B, that where A points to B. And you can see down here how GraphViz will produce an automated layout for this graph. So we could have B pointing to C, and say C pointing back to A, right? And GraphViz would produce again a nice graph. So if we wanted to visualize, Alice here, we would say that, well, we have a node called Alice, and the label of that node is Alice, and then we have Alice that likes, let's not go with Alice because Alice only likes people, she's nice. Let's go with maybe Don. Okay, so Don is linked to Bob, and Don is also linked to Fred. Okay, so let's make our graph a little bit nicer. So let's say that our nodes, we have we'll have a font size 10. 10 is too small, let's go with 11. And we'll have a font family. I'm not getting that right. Give me a sec. It's called font name, not font family. Okay, and let's say that they are also rectangles by default. And let's say that their style is filled, and the fill color is white. Okay, so we have a decent looking diagram here. So now what we need to do is we need to distinguish between these two edges, right? Remember, since they represent different relationships, it's good to be able to visually distinguish between them. And what easier way to do that rather than to give them a different color? So we'll say that this color is green because Don likes Bob, but this color will be red. Okay, and now we have our like prototype. Now we want to produce these graphs automatically from the model every time the model changes. So in order to do that, we'll need to define a model to text transformation. So I will define a model to text transformation called social network.egx, and I will also define a template here called person to graphviz.egl. Okay, so in my social network EGX, I want to say that I have a rule which is called person to graphviz, and that transforms every person. We don't need the target, using the person to graphviz.egl template into a view that lives in the path social network, p.name. Okay, and its format is graphviz dot. And if these kind of strings look like magic, they're all documented in the article what they actually mean. Okay, so now I'm going to take my prototype and put it in the template. Good. We don't care. Okay, so I'm now going to change this endpoint. So here I have this processing instruction that says that every time the model changes, render it using EGX and using this particular template. I'm going to change that to Picto Live. Okay, good. So now you can see how for my social network I have 6 views. But because this is just static text, I'm getting the same content in every view. We have to change that, right? We have to make these graphs specific to every person. So how do we do that? Let's put everything here. So we have a p variable which represents the person that this template is executed for. So first thing I'm going to do is I'm going to say, well, this is not done. This is actually p.name. And this is also p.name. And then here I want to generate one of these for every person that from every other person that our person p likes, and one of these for every person that they dislike. So I'm going to create a for loop and say for every other in p.likes, because if we look at our meta model, person has a likes reference. I'm going to generate one of these, and then I'll just copy because I'm lazy and that's why I like text, and go dislikes and then go red. Okay, so again here this is not Don and Bob, this is p.name and other.name. Okay, and I'll copy that here too. Okay, so now if we switch to our FlexMI, we can see how now we get different views for every person. And if we were to add another person, we would get another view here. Okay, so how do we then generate this big diagram of the overall social network? We need another rule. So we'll just copy that, create another rule and call it social network to graphviz, and I am actually going to reuse the same template, because this template already does a lot of what I wanted to do. However, I don't want to do this now for one person. I want to do this for many people. So what I'm going to do is I'm going to define an extra parameter here. First of all, I'm going to transform a social network, the entire social network, and I want that diagram to live right here, so there's no need for the second component of the path. And I'm going to add another parameter called people, which in this case is person.all. So all the people, I want to include all the people of the social network in this diagram. Or even better, if I want to be more precise, s.people. Okay? So now I'm going to modify my template and make use of the people, of the new people variable. Before I do that, I need to update here as well and say that, well, this will also put people, which in this case is just a sequence with one person, which is P, the one we're running the transformation for. So I'll save that, I'll go here and I say that I don't want to do this just for one person anymore, but I want to do this for every P in people. Okay, I'm going to close this here, indent this over here. Okay, and if everything goes well, now I have my social network level diagram too. Now this doesn't look very good. Over here I'm using the dot layout engine of GraphViz. GraphViz contains a number of layout engines. I'm going to use a different one called Circo, which creates circular kind of diagrams. I'm going to save that, go back here, refresh, and here's how we can produce that layout. GraphViz has other engines as well, and again, it's quite a big tool in its own right. It has lots of capabilities. We can create very complex visualizations using GraphViz. So what I'm going to show you now is a visualization we have produced for eCore meta models. So this is eCore.eCore, so the meta model of eCore itself, and we have produced visualizations using Picto, because essentially what you get here is a web browser. You can produce GraphViz content, but you can also produce, for instance, just straight HTML, or you could produce SVG in your model to text transformation. So if we look at the source code behind this view, this is actually making use of Google charts in order to produce a bar chart that says how many classes are there in our meta model and how many attributes and how many references. This view makes use of a 3D JavaScript library that shows the hierarchy in our meta model. So we can use Picto to produce quite elaborate visualizations, just because we can build on top of all the nice things out there that can render into a browser. This is our useless spaghetti diagram, right? Which shows why it's important to be able to produce contextual views of models. This represents the entire meta model. And here we have one diagram. We're generating one diagram for every type. So if we go to eClassifier, we can see that an eClassifier is a subtype of eNamed element, and it contains many packages and classifiers. Picto also supports layers, so we haven't seen how to implement them, but they are discussed in the article. So here, for example, we can choose to also show the subtypes of classifier So we can see new stuff have popped up. Also, in Picto, we can define links between views. So here we link classes that are not in focus, so the yellow classes of these diagrams, to the diagrams of the respective classes. And we also link classes that are painted in green, so the class of focus, back to the editor. So click here and I get to the editor of ecore.ecore. Just giving you a kind of quick preview of the different features that Picto provides. So here we have a configuration file. In its simplest form, a configuration file just states which transformation needs to be executed, but we can also have custom views in here. So here we define a view called features, which is of type class diagram, and so class diagram refers to the name of one of the transformation rules in Picto. So you'll see here we have a rule called class diagram. So effectively this says run the class diagram transformation rule and pass it this class names parameter. So effectively only show these classes in the class diagram that you will produce. And then if we look at our tree viewer, that indeed produces a features diagram that only contains these 5 classes. And again, here we can have our we can kind of show and hide different layers. Okay, what else? So this demonstrates plant UML. So here we have a small language for representing sequence diagrams. So we have scenarios that have steps, and then these can be interactions with participants, or they can be loops, or they could be kind of alternative blocks. So we can use that to create essentially sequence diagrams, and then we lay out these sequence diagrams using plant UML. So if you look at first of all, we can generate contextual sequence diagrams, which means that we can focus on individual parts of the process. We can say, well, let's focus on what happens when the pin of the customer is invalid, and that kind of produces a layout that hides everything else that is not relevant to this step. Or what happens, how do you get to balance display? You first need to enter a valid pin, and then that gets you to balance display. Or what happens if you have insufficient funds when you try to withdraw money from an ATM. Some other examples. So let me register that. So here we have an example where Picto is used to produce diagrams of safety arguments, and we have things like goals and contexts and so on and so forth. And we can also have, because this starts becoming a mess for a large system, we can also have kind of auto-generated views at the goal level, so that we can explore every goal in the argumentation process individually. Just to show you how complex we can go with if we decide to, for example, use SVG. Here is another example. What we have here, right? So what we have here is a small language for defining vehicles that have wheels and engines, and then we have diesel engines and petrol engines and so on and so forth. And in this visualization we kind of change the size of, so this is like a top-down view of a car. These are the wheels, this is the front screen, the back screen, the engine, etc. And here we can change the length of the car depending on how many wheels it has, for example. And the way we do that is our template now doesn't produce dot or plant UML, it produces straight SVG, where we can have dimensions and so on and so forth. Okay, let me check the chat, see if there are any questions. No. Yes, please.
So I will do this by voice. So what is the relation of this visualization with model fragments and model slice?
It is effectively a form of model slicing. So it uses model slicing to produce smaller subsets of the model and then visualize them in one go.
And my second question is, so you provide visualization with these tools, but you are still, let's say, locked to editing the textual representation of it?
Not really. So Picto works with any, in terms of EMF lingo, with any editing domain provider. So you could have a graphical editor, for example, for your language, and you could use Picto to generate additional visual representations. Okay. So it's not bound to FlexMI. And then it's extensible, so it can be attached to other types of editors. Plus, it can run in a standalone mode with whatever models Epsilon supports. So I don't know where I have it. Yeah, I think I have an example here in the social network. Social network standalone. Okay, so here, this is not bound to any particular editor. It can visualize this model, which is of type EMF, and it has this name, this metamodel URI, this model file. So for example, we could use exactly the same technique to visualize a Simulink model, or to visualize a Hawk model index. Whatever type of model is supported by, or a spreadsheet, for instance, whatever type of model is supported by Epsilon can be configured within Picto, and then it's independent of an editor. It just kind of loads the model as any other program would. Good question. I should have mentioned that. Okay, good. Okay, as I said, everything that I've shown is documented more extensively in this article on the Epsilon website, and I invite you to go and have a look before this afternoon's practical. And I think with that, we come to the end of this lecture. So just a quick recap: we talked about the importance of graphical modeling. We talked about some principles for designing effective graphical syntaxes, and then we went through some of the main features of the Picto tool for generating graphical views from textual and models in general.